In the previous lecture we were discussing about some of the basics of electrical double layer theory, and in the process we came in the context of the Gauss law, and based on that we derived the Poisson equation. So, the Poisson equation this is the Poisson equation with which we finished our previous lecture, and we concluded that this equation has to be combined with the Boltzmann distribution to solve the potential distribution within the electrical double layer. How that can be done, we will get into that now. So, let us say psi be the potential in the electrical double layer across the electrical double layer. So, E is equal to minus of grad psi. This is the definition of electric field. It is the by definition minus of gradient of the electrical potential. So, it becomes now this being a general problem, we can consider a special case where the electric field distribution is one dimensional. That means the electrical field only varies along the y direction, where y is the direction perpendicular to the solid boundary. So, we can write, not only that, we also assume that we have a solution for which epsilon is a constant. Epsilon is the permittivity of the solution. Typically for an aqueous solution it is around 80 times that of epsilon naught, which is the permittivity of the free space. So, with that we can write the Laplacian becomes the second derivative with respect to y. Next, the charge density. So, let us say that n plus is the number density of positive ions and n minus is the number density of negative ions. For example, this may be Na plus number density, this may be Cl minus number density. So, Boltzmann distribution, which we derived in the previous lecture, it tells that n plus is equal to n0, where n0 is the bulk concentration, where Z is the valency of the positive ions. You can write Z plus, and n minus is n0 e to the power minus Z minus E psi by kBT. Now, as a special example, let us consider a Z is to Z symmetric electrolyte. What does it mean? If you take NaCl, in NaCl when it breaks up into Na plus and Cl minus, then Z plus is 1 and Z minus is minus 1. Okay. So, Z is to Z means whatever is the valency of the positive ion, the same is the valency of the negative ion, but you have to give a minus sign to take into account that the other ion has opposite charge. So, if you have Z is to Z, then n plus is equal to n0 e to the power minus z e okay. So, here we have substitute plus z, here we have substitute minus z, okay. So, then this equation will boil down to okay. Now, before that okay. So, this is the charge density, this we have written as the net charge density is what? The difference between the positive and the negative charges. So, technically rho e is defined as this one. Now, here z plus is z and z minus is minus z. So, if you take z common, it becomes e z e into n plus minus n minus, that is what is written here. So, then this can be written as okay. So, now let me rub this part of the board so that we can write better, clearer. So, epsilon d2 psi dy2 So, this by definition is sin hyperbolic x is e to the power x minus e to the power minus x by 2. So, e to the power minus e to the power x minus e to the power minus x is 2 sin hyperbolic x, that is what is written. So, this equation is the so called Poisson-Boltzmann equation. Now, this equation is a non-linear equation, and although there are techniques for solving this equation, but just for the sake of convenience we will work out the solution for a special case when this becomes a linear equation, and that is there. See, the non-linearity is because of this term. So, this term can be linearized when this is small, when ZE psi by KBT is small, is much less than 1, then sin H is as good as ZE psi by KBT. This you can easily do by expanding sin h in terms of exponential series and retaining only up to the linear term in the exponential series. So, this is known as Debye-Huckel linearization. So typically now you can argue that what is the typical physical value of the potential? The typical physical value of the potential that keeps this within this limit is around 25 millivolt. So if the zeta potential, the maximum psi is zeta potential. So if the zeta potential magnitude is less than 25 millivolt, you can safely apply this linearization. So under that case, so now before solving this equation can be solved very easily, but even before solving this equation we can make an estimation of how thick the electrical double layer is. So to do that we will do an order of magnitude analysis. So order of magnitude of this is epsilon zeta by lambda square, where lambda is a characteristic length of the EDL, okay, and zeta is maximum psi. So d2 psi dy2 is what? d dy of d psi dy. So it is some characteristic psi divided by square of some characteristic length. So the characteristic length lambda, this is called as Debye length. This is the characteristic length of EDL. This is not actually the length of EDL, this is the length scale, you know, the order of magnitude of the EDL. So this and this is of the order of 2n0 z square E square zeta by kBt. So from here, since these two terms are equated, we can write 1 by lambda square is of the order of 2n0 z square E square by epsilon kBt. Okay. So I will show you that if you do some calculations based on what is, so in this what you can vary, this n0 you can vary, which is the concentration of the salt solution. Z also you can vary, but normally you know it will be 1, 2 like that, monovalent, bivalent. E is the protonic charge, is constant, epsilon is the permittivity of the solution, which is also not varying that much, Kb is Boltzmann constant, and T mostly we are doing in the room temperature. So n0 is the parameter, and you can see here that lambda will be varying with 1 by square root of n0 given all other parameters are constant. So now I will show you a slide where I will show you what are the typical values of lambda based on the concentration. So you can see the concentration of the solution, capital M is molar, that is moles per liter. So if it is 10 to the power minus 6, which is micromolar, this kind of solution we normally do not use, but in that case it is around 300 nanometer, but typically it is around millimolar to, so millimolar to molar. So millimolar, that is 10 to the power minus 3, the Debye length is around 10 nanometer. So this is the very typical rough idea, you know, as a biomicrofluidics engineer it is very important that you have a rough feel of these numbers. So for a typical millimolar solution the Debye length will be around 10 nanometer. So if you imagine that the channel, the micro channel is 10 micron, then only a small portion close to the wall will be having this Debye layer. Outside that the surface charging effect will not be felt. Okay. Now how do you solve this equation? The solution of this equation is quite simple, and I will of course give you the idea of how to solve this equation, but I will not get into the solution for all general cases because it takes time. So, let us say psi equal to e to the power my be the trial solution. This equation is basically a second order homogeneous ordinary differential equation. So, m square epsilon e to the power my is d2 psi dy2 so m square minus so this is 1 by lambda square. So that means m is equal to plus minus lambda. So the solution is psi is equal to C1 e to the power lambda y, sorry, plus minus 1 by lambda. So plus minus plus C2 e to the power minus 1 by lambda y. Okay. This C1 and C2 you can calculate from the boundary conditions. So for example, if you have an open surface like this, then at open surface means fluid is open in this direction. So here you can write that at y equal to 0 psi is zeta potential. This is an example. At y equal to 0 psi is zeta, and at y tends to infinity psi will be 0. So at y tends to infinity psi equal to 0, this will give you C1 equal to 0. So psi is equal to C2 e to the power minus y by lambda, and at y equal to 0 psi equal to zeta, that means psi equal to zeta into e to the power minus y by lambda. So it is a exponential decay of the potential, but if it is a channel, you know, the boundary conditions will be different. If it is a closed channel, and accordingly the solutions will be different. So if you look into the slide, here I have given a solution for psi with the condition that psi is equal to zeta at y equal to 0 and y equal to 2h, which are the boundaries of the bottom plate and the top plate, and accordingly the solution will be given by this cos hyperbolic function, which is the combination of e to the power x and e to the power minus x. Sin hyperbolic was e to the power x minus e to the power minus x by 2, cos hyperbolic is e to the power x plus e to the power minus x by 2. Okay. So the next concept, so what we will do with this electrical double layer concept, how can we use this to drive the flow? So to understand that, we will consider a mechanism called as electroosmosis. So what is electroosmosis? Let us say that you have a channel with negative surface charge. So bulk will have more positive charge, and then you apply a bias, here positive bias and you have a negative bias. So when you apply this bias, these negative ions will be driven towards this, positive ions will be driven towards this negative electrode. So when this is done, these ions are not alone, right, these are hydrated by water. So because of the viscous interaction between the ion and the water, water will also be dragged in this direction, and that is how a flow will be created. So this is the physics of electroosmosis. Now we will try to understand that how we can translate this physics into mathematics. How can we write an expression for the corresponding velocity profile? So to do that, let us assume that you have a parallel plate channel, that is a rectangular channel with the width much higher than the height, and let us say this height is 2h, and at a section y we take a strip of width dy. If there is no pressure gradient which is acting on this fluid, that means the pressure here and pressure here are the same and the zeta potential is uniform, then the only forces are the resisting viscous forces and the driving electrical forces. So, the resisting viscous forces, so here the viscous force is so let us say that this boundary, whatever is the fluid below it, that is moving at a faster rate because it is closer to the center line. So, it is trying to pull the fluid in the forward direction. So, this is the force exerted by the bottom fluid on this element. Similarly, the top fluid is closer to the wall, so it is trying to create a drag which will try to slow down it. So, if we call it as tau, this we call as tau plus d tau. So, let us say this length of the element is dx. So, this is tau into dx. Let us say width of the channel is 1. So, this is tau plus d tau into dx into 1. There is also a body force. What is the body force which is pulling this? Let us say Ex is the electric field along the x direction. So, this is not the induced electric field, this is the applied electric field. So, here there are two types of electric field, one is induced in this direction due to electrical double layer, another is applied along the x direction to make the fluid flow. A combination of these two is actually making the fluid flow. So, if you have now Ex as the electric field, the body force due to that is rho e into Ex per unit volume. So, now if you multiply this with the volume, this is dy into dx into 1, this is the total force. Now, if the flow is fully developed, all forces are balanced. So, that means d tau, tau plus d tau into dx minus plus tau dx plus rho e into Ex into dy dx, this is 0. So, you can write that this one minus d tau dy plus rho e into Ex equal to 0. Okay. Now, what is this tau? Tau is equal to minus mu du dy, where u is the velocity along the x direction. So, why minus mu du dy? Because if you write tau is equal to mu du into d of d say of some coordinate y without the minus sign, then that coordinate has to be outward normal to the wall. Here the y direction is like this, which is opposite to this. So, that is why the minus sign here. Okay. So, you have this is our governing equation. Now, what is rho e? This is from the Poisson equation. d2 psi dy2 is equal to minus rho e by epsilon. Okay. So, we can write Okay. So now let us make an order of magnitude analysis and see what is the velocity. So this is of the order of, let us call it a u characteristic velocity, which is also known as Helmholtz-Smoluchowski velocity. So UHS by lambda square, this is of the order of minus epsilon zeta Ex by mu, forget about minus, just order of magnitude wise this, plus or minus we will see later on. So UHS is of the order of epsilon zeta Ex by mu, and normally we give it a minus sign. Why minus sign? Because see, if you have a positive bias here and a negative bias here, then what is the electric field? Electric field is minus of the gradient of the potential. So the electric field is positive E. The surface charge, if it is negative, then zeta potential is negative and it is driving a flow in the positive direction. So minus E, plus of E and minus of zeta is driving a positive U. To adjust for that, you have a minus sign here. Okay. So with this conceptual understanding, let us solve this. So du dy if you draw the channel like this, at the center line of the channel you have both du dy and d psi dy 0, that means C1 equal to 0, and then if you integrate it, u minus epsilon Ex by mu psi is equal to C2. At the wall u is 0 at the wall, this is no slip, and psi is zeta. So you have C2 is equal to minus epsilon zeta Ex by mu. So u okay, from this equation by putting C2. So this is nothing but this UHS. So u by UHS is equal to 1 minus psi by zeta. So what kind of velocity profile it is? Psi will be 0 outside the electrical double layer, and let us say this is the channel. The electrical double layer, this is micron, electrical double layer is say within 10 nanometer. So within 10 nanometer only you have this variation, outside that psi is 0, so u is UHS. So the velocity profile is something like this, almost uniform. So this is a great advantage for biological applications, because for a pressure driven flow you have a parabolic velocity profile. So if you have a reaction site at the wall, the sample which is flowing, the sample will have a tendency to go along the center line, but it will not come easily to the wall. But if you have a uniform velocity profile, the biological sample will come easily to the wall and do the biological reaction. So this has an advantage. But any advantage is also associated with a limitation. The limitation is that you, in this situation, you can have a Joule effect, because there is a current flowing through the system, there is a heating effect. Because of this, some biological samples which are thermally labile, they can be disintegrated, and that may be a detrimental thing in a biological application. So one cannot use very large electric field. So with this, so I will go through this slide to give you a basic idea of what are the typical values. So, zeta potential is 25 millivolt, epsilon is 80 into the permittivity of free space, mu is 10 to the power minus 3 Pascal second, electrical field is typically along x is typically 10 to the power 4 volt per meter. So, the velocity that you get out of this is of the order of 10 to the power minus 4 meter per second. So, this is what is typically what you get, and this is the velocity profile how it looks if you draw it, almost uniform except in a thin region close to the wall. So, this is the comparison between electroosmotic and pressure driven flow. So, you can see here that if the pressure driven flow is having a parabolic velocity profile and electroosmotic flow is almost a uniform velocity profile provided the zeta potential is constant, and therefore, it has several advantages. So, pros and cons of the electroosmotic flow. Advantages: velocity does not depend on geometrical dimensions, it is minus epsilon zeta E by mu, does not depend on the channel dimensions. There are no moving components involved and you can integrate this easily with an electronic or electrical circuitry. But the disadvantage is that the zeta potential is a strong function of the chemistry. So, there is a strong dependence on surface chemistry and properties of the solution. Not only that, the uniform velocity profile will become non-uniform as soon as the zeta potential becomes non-uniform, and that may be the case if the surface is inhomogeneous. And the third point is the Joule heating, which I have already mentioned. Next, in the next couple of minutes I will try to go through some other electrokinetic effects very briefly. One is streaming potential. So, streaming potential, what you do is instead of applying an electric field you apply a fluid flow. So, when you apply a fluid flow through a pressure gradient, then because of the electrical double layer effect there are ions in the solution, these ions will be migrating in a particular direction and a potential will be created across the channel. So, here in electroosmosis the input is axial potential and output is flow. In streaming potential the input is a flow due to pressure gradient and output is a potential, and you can tap that potential to harness power, and we will discuss later on in one of our lectures in microfluidics for healthcare that how can this be used to energize point of care diagnostic devices. Electrophoresis, it is a very fundamental process which is basically the movement of a charge due to electric field. So, if you have an electric field you can drive the charge q by applying a force which is q into the electric field. So, you can in biomicrofluidics it is important because DNA has negative charge. So, you can apply electric field to move DNA and that is known as DNA electrophoresis. There is also a terminology called as dielectrophoresis where the difference in polarizability between a particle and a solution in a non-uniform electric field gives rise to a net force on a particle. So, the two things are required, one is non-uniform electric field, second is the difference in polarizability of the particle and the solution. So, by using this you can actually apply a force and make a particle move. AC electroosmosis. So, with the DC electroosmosis which I have explained earlier, it is associated with overheating problem and bubble formation due to local electrolysis at the electrode. So, this can be prevented by using a AC bias instead of a DC bias, and if you have an AC electric field on a surface then the surface charge also changes with time and the force and the electric field also changes with time. Combination of charge and electric field which is shown in the diagram here is such that that is always acting in a particular direction. The charge in a cycle changes, the electric field in a cycle changes, but the product does not change in the direction. So, AC electroosmosis is a very important process. And finally, I will talk about another electrokinetic effect called as electrothermal flows. So, in electrothermal flows, if you create a thermal field in the sample or a thermal field is already there in the sample that can give rise to gradients in electrical properties. So, you can see here that there is a property permittivity and there is a gradient in permittivity which can give rise to an additional body force beyond the charge density times the electric field. So, this additional body force is because of the variation of permittivity with temperature, and that therefore is created when you have a temperature gradient in the fluid. So, this may be very important for many biological applications. This has not yet been harnessed so far for many biological applications, but using the natural property gradient due to temperature gradient you can actually modulate and control a flow, and that flow can be utilized for microfluidic purposes with biological applications as a specific example. So, to summarize, in this lecture we have discussed some basic electrokinetic effects. We have primarily focused on electroosmosis, but we have also discussed on several other effects, and till now we have therefore studied the pressure driven flow, the surface tension driven flow, the rotational microfluidics and electrokinetically driven flow. Now, how do you actually use these for healthcare applications? We will see this later on towards the end of this course. Thank you very much.